Ocean layering. Ocean surface temperatures range from -2 degrees Celsius in polar waters to 30 degrees Celsius in equatorial regions, with the average surface temperature being 15 degrees Celsius. Ocean water temperatures, however, decrease significantly with depth. Thus, deep ocean water is always cold, even in tropical oceans. Figure 15-15 shows a typical ocean temperature profile, which plots changing water temperatures with depth. Such profiles vary depending on location and season. In the temperature profile shown here, beneath roughly 100 meters, temperatures decrease continuously with depth to around 4 degrees Celsius at 1 kilometer. The dark waters below 1 kilometer have fairly uniform temperatures of less than 4 degrees Celsius. Based on temperature variations, the ocean can be divided into 3 layers, as shown in Figure 15-16. The first is relatively warm, sunlit surface layer, some 100 meters thick. Under this is a transitional layer known as the thermocline, which is characterized by rapidly decreasing temperatures with depth. The bottom layer is cold and dark with temperatures near freezing. Both the thermocline and the warm surface layer are absent in polar seas, where water temperatures are cold from top to bottom. In general, ocean layering is caused by density differences because cold water is more dense than warm water. Cold water sinks to the bottom while less dense. Warm water is found near the ocean's surface. Water masses. Temperature of the bottom layer of water is near freezing, even in tropical oceans, where surface temperatures are warm. Where does all this cold water come from? The source is Earth's polar seas. Recall that high salinity and cold temperature causes seawater to become more dense. When seawater freezes during the Arctic or Antarctic winter, sea ice forms. However, salt ions aren't incorporated into the growing ice crystals and accumulate beneath the ice. Consequently, the cold water beneath the ice becomes saltier and denser than the surrounding seawater, and this saltier water sinks. This salty water then migrates towards the equator as a cold, deep water mass along the ocean floor. Other cold, deep water masses form when surface currents in the ocean bring relatively salty, mid latitude or subtropical waters into polar regions. In winter, these waters become colder and denser than the surrounding polar surface waters, and thus they sink. 3 water masses account for most of the deep water in the Atlantic Ocean. Antarctic bottom water forms when Arctic seas freeze during the winter. With temperatures below 0 degrees Celsius, this water mass is the coldest and densest in all the oceans, as shown in Figure 15-17. North Atlantic deep water forms in a similar manner offshore from Greenland. It is warmer and less dense than Antarctic bottom water and thus overrides it. Antarctic immediate water forms when the relatively salty water of the Antarctic Ocean decreases in temperature during the winter and sinks. Being slightly warmer and less dense than North Atlantic deep water, Antarctic immediate water overrides the other 2 water masses. While the Atlantic Ocean contains all 3 major deep water masses, the Indian and Pacific Ocean contain only 2 deep Antarctic water masses. You'll model water masses in the GeoLab at the end of this chapter. In the next section, you'll learn about the water movement in the oceans. 15.3 Ocean Movements. Oceans are never completely motionless. Their most obvious movement is the constant motion of waves. A wave is a rhythmic movement that carries energy through space or matter, in this case, ocean water. Ocean waves are generated mainly by wind flowing over the water's surface. As an ocean wave passes, the water moves up and down in a circular pattern and returns to its original position, as shown in Figure 15-18a. Only the energy moves steadily forward. The water itself moves in circles until the energy passes, but it does not move forward. Wave characteristics. In the open ocean, a typical wave has the characteristics shown in Figure 15-18b. The highest point of a wave is the crest, and the lowest point is the trough. The vertical distance between crest and trough is the wave height. The horizontal crest to crest distance is the wavelength. The wavelength determines the depth to which the wave disturbs the water. That depth, called the wave base, is equal to half the wavelength. The wavelength also determines the speed with which the wave moves through deep water. Wave speed increases with wavelength. Wave height. Wave height depends upon three factors: wind speed, wind duration, and fetch. Fetch refers to the expanse of water that the wind blows across. Large storm waves can be much higher than average. For instance, hurricane can generate waves more than 10 meters high. The greatest wave height ever recorded was more than 30 meters. This monstrous wave occurred in the North Pacific. Breaking waves. As ocean waves reach the shallow water near shorelines, they begin to lose energy because of friction with the ocean bottom. This causes the waves to slow down. As the water becomes shallower, incoming waves crests gradually catch up with the slower wave crests ahead. As a result, the crest to crest wavelength decreases. The incoming waves become higher, steeper, and unstable, and their crests collapse forward. Collapsing waves, such as those shown in Figure 15-19, are called breakers. The formation of breakers is also influenced by the motion of wave crests, which are less affected by friction than the wave troughs and thus overrun the troughs. The collapsing crests of breakers moving at high speeds towards shore play a major role in shaping shorelines. You'll learn more about breakers and shoreline process in the next chapter. Tides. Tides are the periodic rise and fall of sea level. The highest level to which water rises is known as high tide, and the lowest level is called low tide. Because of differences in topography and latitude, the tidal range, the difference between high tide and low tide, varies from place to place. In the Gulf of Mexico, the tidal range is less than 1 meter. In New England, it can be as high as 6 meters. The greatest tidal range occurs in the Bay of Fundy between New Brunswick and Nova Scotia, Canada, where it is as high as 15 meters. Generally, a daily cycle of high and low tides takes 24 hours and 15 minutes, as shown in Figure 15-20. The daily cycle can follow three distinct patterns. You'll learn about tides in the problem-solving lab on this page. Causes of tides. The basic cause of tides are the gravitational attraction among Earth, the Moon, and the Sun, as well as the fact that gravitational attraction decreases with distance. Consider the Earth-Moon system as shown in Figure 15-21. The Moon does not actually orbit Earth. Rather, both Earth and the Moon orbit around a common center of gravity. As a result of their motions, both Earth and the Moon experience different gravitational forces. The unbalanced force generates tidal bulges on opposite sides of the Earth. The gravitational effect on Earth's oceans is similar to what happens to the liquid in a coffee cup inside a car. As the car goes around a curve, the liquid sloshes towards the outside of the curve. The sun's influence. The gravitational attraction of the sun and the Earth's orbital moon around the sun also generate tides. However, even though the moon is much smaller than the sun, lunar tides are more than twice as high as those caused by the sun because the moon is much closer to Earth. Consequently, Earth's tidal bulges are always aligned with the moon. Although the sun's tidal effect is smaller than that of the moon, it is still significant because of the sun's great mass. Depending on the phases of the moon, solar tides can either enhance or diminish lunar tides, as illustrated in Figure 15-22. Notice that large tidal ranges called spring tides occur when the moon is either full or new. These phases of the moon occur when the sun, the moon, and the earth are aligned. During spring tides, high tides are higher than normal and low tides are lower than normal. Small tidal ranges called neap tides occur when there is a first or third quarter moon. During these times, the sun and the moon and earth form a right angle. During neap tides, high tides are lower and low tides are higher than normal. Spring and neap tides alternate every 2 weeks. On average, spring tides are 3 times higher than neap tides. Ocean currents. Recall the discussion of Antarctic bottom water in the previous section. The movement of Antarctic bottom water is an example of an ocean current. In this case, the current is called a density current because it is caused by difference Differences in the temperature and salinity of ocean water, which in turn affects density. Density currents move slowly in deep ocean water. More noticeable than underwater density currents are wind-driven surface currents. Surface currents affect mainly the upper few hundred meters of the ocean, and they can move as fast as 100 kilometers per day. Driven by Earth's global wind system, surface currents follow predictable patterns. In the northern hemisphere, tropical trade winds blow from east to west. The resulting tropical ocean currents also flow from east to west. In northern mid-latitudes, the prevailing westerlies and resulting ocean currents move from west to east. In northern polar regions, polar easterly winds push surface waters from east to west. Uh, Gyres. If Earth had no land masses, the global ocean would have simple belts of easterly and westerly surface currents. But the continents deflect ocean currents to the north and south, so that closed circular current systems called gyres develop, as shown in Figure 15-23. There are five major gyres: the North Pacific, the North Atlantic, and the South Pacific, and the South Atlantic, and the Indian Ocean. Because of the Coriolis effect, which you learned about in Chapter 12, the gyres of the northern hemisphere circulate in a clockwise direction, and those of the southern hemisphere circulate in a counterclockwise direction. The part of all gyres closest to the equator move toward the west as equatorial currents. When these currents encounter a landmass, they are deflected toward the poles. These poleward flowing waters carry warm tropical water into higher, colder latitudes. A well known example of a warm current is the Kuroshi or Japan current in the western North Pacific. After these warm waters enter polar regions, they gradually cool and deflect by land masses, move back toward the equator. The resulting currents then bring cold water from higher latitudes into tropical regions. An example of such cold ocean currents is the California current in the eastern North Pacific. You'll learn more about currents in the Science in the News feature at the end of this chapter. Upwelling. In addition to moving horizontally, ocean waters move vertically. The upward motion of ocean water is called upwelling. Upwelling waters originate from the bottom of the ocean and thus are cold. Areas of upwelling exist mainly off the western coasts of continents in the trade wind belts. As Figure 15-24 shows, the trade winds blow surface waters offshore, and the surface water is replaced by upwelling deep water. Upwelling waters are rich in nutrients which support abundant populations of marine life. Consequently, some of the world's richest fishing grounds are found off the coasts of Peru and California.